All right, so the next question is the real numbers. What about the set of real numbers? Well, it turns out that the set of real numbers is not countable. It turns out that it's impossible to create a bijection from positive integers or natural numbers to the set of real numbers. That's impossible. You can't count them because there's just too many. So I'm going to show you a proof of that. This is a proof which is going to use the strategy of proving by contradiction. And this proof was first published by Georg Cantor, who I mentioned as sort of like the granddaddy of set theory in general. And so it is sometimes referred to as Cantor's diagonal argument. Now, I want to mention that there's a really great video on YouTube done by Michael Stevens of Vsauce. It's a video about the Banach-Tarski paradox, and I'll put a link in the video description of this video about that. If I forget, then please remind me, or you can Google it. But the Vsauce video about Banach-Tarski paradox has a very nice. It goes through this proof, actually, very nicely, and then it goes on to explain the Banach-Tarski paradox extraordinarily well, and in a way which I think is very easily digestible, or relatively easily digestible for you. And that's why I would encourage watching that video if you want. It's fun. It's certainly not like directly related to stuff we're doing in this class, but it is at least tangentially related to stuff we're doing here. I think that some of you might really enjoy it. It's a long one. It's a bit of a long haul. And just to warn you. But anyway, so yes, R is uncountable. Let's prove it. So if we're going to prove it by contradiction, then the way we'll do that is to start by actually assuming that R is countable, and then define the contradiction and conclude that, well, it can't be countable. So that'll be our first line of the proof. We'll say, suppose R is countable. Well, okay, one of the theorems we had earlier is that if you have a countable set, then any subset of that set is also guaranteed to be countable. So what I can say is then, in particular, any subset of the real numbers is countable. And for this proof, we actually want to look at the subset, which is the open interval from 0 to 1. So this is not the set containing two elements, 0 and 1. This is interval notation. So this represents on your real number line, if you have 0 and 1, this is an open interval of that contains all of the real numbers between 0 and 1, not including the endpoints. So that is the set we're going to work with in particular. So if that's countable, there must exist a bijection from the positive integers to that set. So let's let F be that bijection. Right? So let's let F be a map from Z plus to 0, 1, and let's that be a bijection. Okay. Now, what I want to do is basically draw a table of values for that function. Now, there's a little bit of logic here that I'm not going to write out super formally. I'm going to kind of more like just explain it in a way which I think is kind of intuitive. And there's a little bit of like randomness involved here where it doesn't really matter what numbers we end up working with as long as we have some numbers. I'm just going to write some random numbers down, but they could be any real numbers, okay? They could be any real number at all. So, any real number in this interval, 0 to 1. So what I want to do here is essentially write a table of values for this function. So my input n is going to be positive integers, 1, 2, 3, 4, 5, 6, ... So my f of n is going to be a real number in this interval, 0 to 1. Now, that's going to look in decimal format. I can write that as like a 0 point something, right? And even if it's just like 0.1, all right, even if it's just 0.1, I could still put an infinite string of zeros after that, and that would be a valid decimal representation of that number. So we're going to assume that all of the decimal representations in this number can have any number of digits that you want, okay? Because you can always put a string of zeros at the end. But it could be like an irrational number. So maybe the next output, and these outputs are kind of random. It doesn't matter what order they're in or what particular numbers they are. They all have to be different, of course. But other than that, it could be anything. So we could have like an irrational number. Like I'm just gonna start I'm just going to start writing something like random numbers, like that's not random numbers at all. Those are the digits of pi. This is pi divided by 10. So, what other irrational numbers do I know? I don't know what that is. I don't know. I can't. That number is in my head. I actually have no idea why I know that number. Is that? That's not E, is it? No. E is 71828 dot. Okay. I'll stop doing this. This is kind of silly. Let's just make up two more numbers. 7192201 dot and 0.521967 dot. Okay. So the point here is if we have a bijection, then we'll have this list of numbers, right? And this list of numbers is countable, so it's going to go on like this forever. And the claim here is that every real number in the interval 0 to 1 is going to appear in this list. If it's a bijection, it has to be surjective. So every single real number in the interval 0 to 1 is going to be in this list. But here's what I can do. Let's let x be a number that differs, a number whose nth decimal place is going to differ from that of f of n. So for f of 1, for 1, the first decimal place is 1. So, for example, okay, I could have this number be 0.2. And then the first decimal place is going to be 2 because it has to be different from the first decimal place of f of 1. So now, for the second decimal place, it has to be different from that of f of 2. So f of 2 is a decimal place of 1. So I can make that another number. And it can be anything else, but I'm just adding 1 to it, just to make sure it's different. For the next number, I need it to be different from the third decimal place of f of 3. So I take this number, that's 4. I'm going to make this a 5, just to make sure it's different. And then here, for the fourth decimal place, it has to be different from 8. For the fifth decimal place, it has to be different from 2. And for the sixth decimal place, it has to be different from 2, and so on. And so this can just continue like this forever, and you can, just as long as you make sure that this is different from each number in this list in at least one decimal place, it's guaranteed to be a number that is not on this list. So let's have that number be called x. And so what we've shown is that x is not on the list, right? So there does not exist a number n, a natural number n, with f of n equal to x, right? Because it doesn't appear on this list. So f is not surjective. And that, not surjective, that contradicts with our claim that this function should have been a bijection, right? Contradicts that. Now, we knew that a bijection should exist if it is countable. So we were assuming that this is the bijection, or at least a bijection, that works. However, we showed that no matter what numbers I had picked here, I could always create some number which is different from these and therefore isn't on this list. In fact, actually, there's an infinite number of different numbers I could have created because I could have made a different choice for these decimal places. There's like lots of choices I could have done here to make it different. So there's tons of numbers that aren't on this list. So this claim that this function must be a bijection is complete bunk. That's impossible. Therefore, what we've shown is that R is not countable.